I kind of agree with you there, Kimia. I kind of wish the exam was optional, but that's just not it. Um, sorry. Nulio, we spent um, a lot of lectures on that. It's based on the stability of the charged species. Nulio was asking how can we tell a favored equilibrium based on structures of acids and bases? The stability of the charged species is generally it. There's a mouse cursor here, which is just kind of hanging out. There we go. Okay. So last class we ran through. We actually spent 40 minutes talking about other stuff and 10 minutes doing some chemistry. Not going to go through that again. This class we're going to continue going through some of these examples, and I didn't get any emails with any particular examples anyone wanted to go through. So save that up for send it to me by Monday morning. If there are some specific examples you want to go through on Monday, like some concepts that you want to revisit. Otherwise, I'll just keep giving some more types of examples. Okay, so the question here would be give a mechanism and the product of this reaction. So what should jump out to you is you have okay. Hopefully this. Okay, my pen has stopped. I have another pen. Okay, I guess one of my pen batteries is dead. Okay, so what should jump out at you is you have a radical initiator here. And so you should be thinking, radicals are possible. Now to activate this, I need heat or light, and I've got heat. So I've got what I need to do radical reactions, and radical reactions are quite fast compared to doing this ionically, the way we were doing it if there wasn't this stuff, it was just Br2. So again, we're going to have a pre-initiation step here because there is a radical initiator, and a radical initiator is never involved in the propagation steps, and so it's not necessarily initiation. If no heat, no radical. No heat, no light, no radical. You need either heat or light. You need something to break the bonds, otherwise it's going to be a lot slower than just having BR add across double bond. So in this case, again, what I love about an open book exam like this is I can just write AIBN, and if I'm not going to get a ton of questions, what's the structure of that? Because you don't type that into Google. And if you memorize it, good for you, but you don't need to, I think is where I'm going with that. I always was really bad at memorizing this kind of thing, so I'm really sympathetic to those of you who are also bad at memorizing this kinds of thing. Well, the other one we saw was benzoyl peroxide. So we just saw that in a previous example. I don't think I will use. No, it's not. Well, I get to set my own rules. I will not use another. We are not going to use MBS in this course. MBS definitely a thing. Definitely a source of bromine. Just not something I'm choosing to run with because there's enough stuff going on. Those of you who choose or are forced to pursue significant additional organic chemistry classes, yeah, the pre-activation is always the same. Those of you who choose to pursue additional organic chemistry classes will see a whole lot more reagents and things, different things going on. But otherwise, the basics are what we're covering in this course, and that's what this is about. So we have the cyanide radical, or this AIBN radical. It looks for the weakest bond in the entire system, and that is going to be the bromine-bromine bond, because heteroatom bonds are weak, just inherently, they always are. You probably yes, you should, and I should too, and I'm sorry. So yes, Jafer, yeah, your pre-initiation we should have too. Um, Mohammed asks, what kind of content can we expect for our go-to? It's a lot of the chemistry of benzene and a lot of the chemistry of carbonyls as well. It's really kind of, we haven't really done any benzene chemistry at all, so it's a lot of that. It's very, but if you, it's kind of a walk in the park if you have a pretty good understanding of what's going on in this course, because it's really just applying these concepts to new problems. I mean, it sort of makes sense that, yeah, of course it happens that way. Why wouldn't it? Benzene has resonance, and that's what it comes down to. There's not much more to be said about that. So in this initiation step, we made a radical that is involved in the propagation. And we know it's a radical that's involved in propagation because we're going to start drawing propagation. But the other thing is it's something that's kind of above the arrow. It's in one of these reagents. Yeah, the triangle is heat. I think I've said that a few times. So propagation. Word on somebody, an email I sent to somebody did convince me that that is an A there. That is correct. Carbonyl is not on the final. I think I sent out an email about that. I think I've said that about HV is light, Mohammed, not HF. But I think, yeah, I did send out an email. Yeah, no worries. HF is hydrogen fluoride. Okay, so this is why I have this example here, is for this precise step. So we've got two options. Bromine radical, carbon radical. Then where does the other radical go? We have two options. We can put the bromine here, and we can generate a radical there. Or so this is where you do need to be careful where I'm saying like, hey, radicals follow all the same rules as carbocations, except when they don't. So if this was a carbocation, we would definitely put the bromine here. We would definitely select this one because we'd have a positive charge here. It would be resonance stabilized by the methoxy group. That would be awesome. But this isn't a carbocation, it's a radical. And so if we try and draw a resonance here, just give it a go. Like, yeah, I can draw a resonance. It all looks good. And we have that. It's all neutral. Does anyone have a problem with what I just drew? Well, the radical wants more substituted carbons because of same kind of hyperconjugation. There we go. Keith says exceeds octet. Yes, that oxygen has 9 electrons around it. Now, why is that a problem? There's nothing magical about the number 8. It's because the 8 comes from something. I like where you're going, Deanna. Yeah, good. So Keith, Miriam, I think Deanna, you're going in there. Adriana, you guys are all right. You don't have enough orbitals, right? You only have 4 orbitals on your valence. And if you do what we just did here, you'd have one orbital making a single bond, a second orbital making this pi bond, a third orbital making this sigma bond, a fourth orbital with this lone pair, and a fifth orbital with this electron. And you don't have 5 orbitals. So this resonance is not possible. It's really tempting to try and do it. It doesn't exist. So this electron here is not stabilized by resonance. So this one is more stable. Because tertiary radicals, somebody up there pointed out that, hey, we like the more substituted carbon. So this is what's formed. So this is what's to be careful about. So what I really want to highlight here is resonance is really good for radicals when they can do resonance. But if the resonance structure is going to force them to be over sticking something with too many orbitals, I don't know what the word is, there probably isn't one for that, then it's wrong. Okay. What do you think? I'm going to turn that question back to you, Bennett. I mean, when can you only do activation, you mean? Julia? Or initiation? Well, you never only do pre-initiation. When do you do it? When you have a radical initiator. When your initial radical you make in a system is not involved in propagation. So the initial radical we made was this. It is not involved in the propagation steps. And so you have this pre-initiation. I do agree this is not, like, there's a little bit of medieval philosophy, angels dancing on the head of a pin kind of thing going on here. Though medieval philosophers do not generally argue about angels on the head of the pin. We saw benzoyl peroxide as well deepen. We saw it was in the previous example yesterday. By yesterday, I mean Wednesday. By Wednesday, I mean March. This has been a very long year. So we end up with this dibromide, and again, we get exactly kind of what we expect. This is propagation step. Would you want us to draw both the structures and then indicate the more stable? No, I only want you to draw the more stable one. So Adriana asked, for the propagation step, would you want us to draw both the structures and then indicate the more stable one, or just the more stable? I only want you to draw the more stable. It's the only one you need for the mechanism. But this is a problem-solving course. You're showing your work. So if you need to draw both out and then indicate the more stable one for you to do your work, then please do. Why? So really good question here from Nicole. Why do the arrows go to the middle of two molecules instead of pointing at something? So with the radicals, they do, because we're kind of mixing them together. So most of the time we're using, throughout this entire course, we've drawn double hook arrows, like standard arrows, and it involves two electrons. And the two electrons went from the source of the electrons to a nucleus. But here what's really happening is two single electrons are kind of joining together to make a new bond. They're not really attacking a nucleus. It's more the electrons are kind of merging together to making two orbitals, or merging together to make a new bond. No, you don't get a three-membered ring because there's no carbocation. So you don't have, because if you think about that, this bromine here doesn't have, it would have to donate an electron to make a bond, and it would need 5 bonds. So you can't do that. Well, let's just finish this off. So the termination. We know we're done propagation because we have gotten back the radical that we started propagation with. That's when you know you're done propagation. So the termination is we need to combine our radicals together. So, we got two different ones in our propagation step. We got bromine and bromine. Bring those together. Yay, we remake Br2. That is a really boring termination step. And you always have to draw all of them because they're possible. They're part of the mechanism. So I can guarantee that somebody will draw this as the product of the reaction. Because they'll go, hey, it's the biggest thing we made. But you don't make very much of it. It's also really easy to screw this up. So if you need to, number your atoms and just kind of make sure that all your atoms are accounted for. Because it is really, really easy, as I just did, to mess this up. And then the last one is er dot. I'm like, the fact that I'm doing a landscape thing does make this a little bit harder. If you're drawing this on all in one sheet on a profile, this normally fits really perfectly on like an 8.5 by 11 piece of paper. So the question, a really good question. Note this is the same thing as that. This is happens to be the product. That's just coincidental. So the question here is, what is the product of this reaction? This is the product of the reaction. The molecule, like the non-radical molecule that is being generated in a propagation. I am clicking too quickly. There we go. That is the product of the reaction. No, there is no stereochemistry. And the reason is, and we saw it when I think we started the first lecture we had on radicals, is the radical occupies a p orbital. So it's like a carbocation. It's between both, it's in both the top and bottom lobe, and it's a 50-50 shot over whether it makes a bond at the top or the bottom if everything else is flat. Yeah, you would get this. You right. So Anita said in this example, wouldn't the top option give us the same product? Yes, it would, but your mechanism would be wrong if you use that. Your answer, you get the right product, but you get it through the wrong mechanism, so you're wrong. Andrew said, aren't all radicals racemic? No. In that there is no other chiral center in this molecule, so there's no bias. But if there was another chiral center in this molecule, you would bias one face or the other because you would have one more accessible than the other. And I think we saw this with a carbocation example a few weeks ago. And it's the same thing here. The carbon where the radical is doesn't care about the top or the bottom face. And in this case, the rest of the molecule also doesn't care. But there could be molecules that do care. So I want to be very careful when you're saying they're always racemic. No, they're not, but the radical is not choosing the stereochemistry. It's not the radical that's determining the stereochemistry. It's something else in the molecule that's doing it. Yeah, you know what, Andrew? I will do one where that matters. I'll come back to that. Maybe I'll just look at that particular step. But let's move on to this example here. So what we want to think about here is, let's say the question was, the question is going to be provide the product and provide a mechanism. So I think this really gets to the heart of a lot of things that we need to be thinking about. Like, if anyone here is looking at this going, I don't know where to start, now is the time to do a lot of assignment questions. If you're looking at this and going, I think I know where to start, and I think I'm going to start by sticking a proton on the H plus on something, you're thinking right. Hi, do you want, my cat is here meowing at me, so I think I'm going to pick her up. There we go. And we can all do it with a cat break. Cat break. There you go. He's over. Some people are saying hi. Nicole wants to say hi. Hi. There. Okay, she's gone. I won't force you to. There's nothing else to look at if the cat's not here. She, meowing at me to get attention, and then I pick her up and she gives me like a good scratch with her back paws, which I think is cheating. My previous cats used to they use their front paws and they would scratch me with those, but that's fair. But these ones bring out their back paws, which is not fair. That's good. Whatever works for you. I don't know. I vastly back and forth between actually thinking about a lot of this stuff in the purely abstract, and thinking about the molecules and how the molecules are doing that, and then switching back and forth with analogies. It's just my brain works that way. Yeah, they get free fed though. They can eat whenever they want, Brendan. Okay, now we're just talking about cats, which I'm all for, but you know, this is not a course on catalysis. We do offer senior fourth year classes on catalysis, which don't have as many cats as you hope. Okay, so we've generated this OH2. No, they're not. My wife would kill me. It's Zoe and Zelda, but that would be good names for cats. One of my colleagues I know, well, I don't. She's not here. She's at a different university. Has a cat named Hydrogen. I don't know why, but it's a good name for a cat. So that's an arrow with water leaving, because water is a good leaving group. It's neutral. You can think of it. Right? So you generate a carbocation. Now, sorry, I went ahead and jumped ahead and did this sort of E1 SN1 thing. And that's because I took a look at these reaction conditions and I went, okay, I'm in protic solvent. I've got lots of heat. I've got a tertiary leaving group once I protonate it. And I don't have any strong bases. Like I'm kind of under acidic conditions. I don't have any strong bases or strong nucleophiles. So the E2, and I don't have a really good leaving group, just an OH on its own. So I'm not thinking E2 or SN2. I'm thinking E1 or SN1, protonate, leaving group, tertiary, carbocation, all good. Now I'm thinking, okay, what's this going to do? What's around? Well, there's terbutanol. And terbutanol is this. And if you go back to your handy chart of balls and sticks and partial balls, this is super ball. Exactly, Bennett, super ball. This is a super ball. So what we're looking for here is you should be thinking, okay, huge, ginormous thingy, not likely to be doing a substitution, hopefully. So it's going to do an elimination, likely. Now you need to identify where is it going to eliminate. And so for that, you need to identify your alpha protons, the protons on the carbons adjacent to the carbocation. So if we don't click too fast, those are them. I don't know if you can hear the purring. So these two, of course, are identical. They're the same proton. Those two methyl groups are the same methyl group. Like there's nothing different about them. Oops, deleted one. This one's different. But hopefully you're thinking this is huge. This is going to do my Hoffman eliminations because it's so big. It's going to get the most accessible proton, not the one that will lead to the most stable double bond, because it is so big it has trouble navigating its way in to get to that hydrogen. And so we would expect that to be the product of this reaction. If you like, you can draw that too, but I'm not keeping track. Okay. Any questions about that? Why not? Reaction goes faster with heat. I think most SN1 and E1s are often driven by heat. It's not strictly necessary. This probably could go at room temperature. You just wait. But heat does make it go faster. I'll always be asking for the major product. unless I have a question where I specifically ask you to show me the multiple products you could get and give me an argument for why one or the other. So Nadia and Amy had the same question. Hopefully I answered your question there, Nadia. Is heat a better indication of E1 over SN1? Heat does favor eliminations over substitutions. Normally that is not the tie-breaking thing. Normally what determines it is the size of the nucleophile, size of the electrophile. Yes. Yeah, you could have put that on the up high card, and like, so could I have put the double bond here? That would be exactly the same molecule. Because you have free rotation around this bond. So this bond can just rotate. And you get that. It's the same molecule. Yeah. The solvent probably takes the least precedent. The solvent helps. You can definitely make it better or worse. But the solvent doesn't normally matter. Normally you're breaking down you're deciding whether you're bimolecular or monomolecular first, and normally you're deciding that by do you have a strong base or strong nucleophile? And if you have a strong base or strong nucleophile, you're leaning towards E2 or SN2. And it doesn't really matter if the solvent's protic or aprotic. Like, aprotic is better, but it's not necessary. It's really about how strong is everything. No. Nicole said, does it matter if double bonds up or down? As I said, no, it doesn't. It's the same molecule. The same proton, it's the same thing. Yes, it does use the same textbook. It has traditionally. Yeah, that's the point. Anyone who's got to do this, I still think this is the best introductory organic textbook. If you keep doing organic chemistry, there's only one other organic chemistry textbook you'll ever buy. And then all the courses basically use that. Like, chemistry is pretty cheap on textbooks. Compared to biology, which wants you to buy a textbook for every fourth year class. Okay. So, let's think about this example here. So the question here would be, provide a series of reactions or a single reaction that takes us from A to B. Now, this is a different question than anything we've seen. This is what ties together a lot of what we've discussed. And so what I want to talk about here is a concept called retrosynthesis. Now, some of you will have been doing this in your mind and not knowing you were doing it. Or, no, we knew you were doing it. You didn't know it had like a name. Because that's basically what the chemistry community did until the 1970s, is I wasn't alive in the 1970s. I'm not that old. But we all did this and just didn't have a name for it. And then somebody came down with like a theory on it and won a Nobel Prize. So good idea is, if you can find something obvious that nobody's given a name for, codify it, formalize it, and you're in good for a Nobel Prize. The overall idea is that when we have a product in a starting material, we can kind of, trying to figure out how to get from one to the other, we can kind of work backwards and forwards simultaneously and try and meet somewhere in the middle. So I think what we need to think about here is, I want to talk about something in terms of handles. And so this molecule, this carbon here is functionalized. It's got something on it. I can do something with that carbon. In the product, this carbon is functionalized. It's got something on it. I can do something with that carbon. Everything else is a CH bond. I can't really do much with those. So the question is, how do I get from A to B? And that's a really hard problem. But I can try and simplify it by saying what I'm needing to do is I need to figure out a way to make this carbon manipulatable from having this carbon manipulatable. And we clearly have a very well-defined carbon scaffold. Like we know where all the carbons are attached to all the other, like the carbons aren't moving around. We know which carbons are which carbons. So what we need to think about is how can we make B and what can we turn A into? Well, we can make B from a double bond. So this is a retrosynthesis arrow. It is a different type of arrow from any other arrow we have used. It is open-ended. And it means basically comes from. Just like the reaction arrow basically means goes to, this means comes from. So this can come from that. And this, how can we make that? Well, I can make that from this, where X is some leaving group. I don't need to find what it is. And so what I've done there from these two steps is I've moved my handle from this terminal carbon to this middle carbon. And in this one, both of these carbons were manipulatable. Now, how do I make this? Well, I can make that. Again, thinking about coming from where I'm going, starting from, and going to, I can make it from that. And now this, I can go forward. There's not a lot I can do, but I can eliminate that, make a double bond. So again, what I'm doing there is I'm saying I can manipulate this carbon and I can do eliminations so I can get both of these carbons. And now for the first time, we have overlap, where this carbon here and this carbon here are both manipulatable. It's the same carbon. We're not quite there yet, but you can imagine this making something with the leaving group there, and this guy coming from something with the leaving group there. And now this and this are equal to each other. So what we're doing here is we're walking back from the product, we're walking forward from the starting material, and we're trying to move our handle, the carbons that we can manipulate, the carbons that have some functionality on them, something we can use them. Double bonds, leaving groups, oxygens, whatever. There's something on those atoms we can use. And we're trying to walk those handles towards each other. And so here we've succeeded in doing that. And we succeeded in meeting in the middle. So the question now is, and you can do this any way you like. You might be able to just run all the way backwards. You might be able to run all the way forwards without having to think too much about it. You might have to go kind of like we did here, kind of going back and forwards. None of these ways are right. None of these ways are wrong. But if I asked you to say, provide a retrosynthesis, and I think I do in one of the assignments, one of the last assignments of the course, you would go, okay, so this becomes this, becomes, I don't know, you pick your favorite halogen, doesn't matter. Maybe you like bromine. Becomes this, becomes, pick your favorite halogen again. And that's your starting material, and that's your product. So what we've done there is we've walked back stepwise. We say I can make this from this, I can make this from this, I can make this from this. And we're just basically walking this double bond along the molecule. Cool. Okay, now how do we go forward? What are the reagents to do this? So what is the synthesis? So I'm gonna leave mechanism out of it today because we've got 15 minutes and I don't have enough time to draw all these mechanisms. And I want to get back to a question that Bennett asked about another example of a radical that isn't racemic. But let's think about this for a second. And we kind of want to flip all those arrows. Yes. Yes, Brendan, they are. I don't know what else to say. Like, none of this is not stuff we haven't covered in the lecture notes today. This has all been covered. We're just putting it together. Like, there is a reason I do this. This kind of thing was actually the kind of thing that made me fall in love with this discipline, was realizing that, hey, this actually has real application. Like, this is the process that we use when I'm trying to figure out how to make a drug. We're kind of walking forwards and backwards. Yeah, it's on YouTube. Everything, all the lectures are on YouTube. I think I'm going to do that forever now. From now on, I think this is something I've learned during the pandemic. Is YouTube is a pretty good tool for this. So, what do we want to do here? Well, we clearly want to do an E2. We could do an E1. That would be fine, but it's a primary carbocation, so an E1 isn't very likely. So we want to do an E2. We don't want to do an SN2. So what's a good way to make sure we do the E2? Well, I don't know. Let's make absolutely sure there is no SN2. So I'm going to use potassium 2-butoxide, which is one of the big bulky guys. So it's never going to do an SN2 in its life. You don't need to go this extreme. But I'm just being like, I'm really not doing SN2. So I make this. Now I want to go to the iodide there. So I want to put an iodide there. I realize, okay, what I want to do is I want to do a Markovnikov addition of iodine. Right? So I'm adding HI. Markovnikov is what I'm trying to do. So how do I do that? Well, how do I add HI Markovnikov? Anyone? Speaking to the blank chat window. Yeah, you just add HI. Yeah, exactly. Good. I really hate writing HI because it's like the I is like an H on its side and it gets very confusing. But right, that's a Markovnikov addition of HI. Cool. So what we're doing here is we're reducing each of these We're reducing each of these problems stepwise and then trying to we're going, this is possible to do. I know this is possible to do. I'll figure out the exact conditions afterwards. Okay. Now I want to do an elimination. And if we have the iodine here, I could eliminate this hydrogen or one of these hydrogens on this carbon. And if I do that, I'm back to where I started, which isn't what I want to do. So I want to go forward. So anyone got a potential base you would want to use for this? Good. OH minus, O ethyl. Yeah. I'd pick something slightly bulkier than those because you don't want a SN2 by accident. So you're picking very, very small bases there. So the OH butyl that Deepan recommended would actually do us the Hoffman elimination, go back to the starting material. So what we want is something kind of ball-like, but not super ball. Yeah. I like Adriana's idea. Keith, exactly. Good choice. It's not the only choice. The ethoxide would probably work too. A lot of the time, but not all the time. It might be a bit messy. This is going to be a little bit cleaner. So what we're doing here is we're doing a Zaitsev elimination. It's a Zaitsev E2. And so we generate this double bond. Okay. Now we want to stick the bromine here. So we have to figure out, okay, what do we want to do? We're doing in addition to a double bond. Is it Markovnikov or anti-Markovnikov? And what reagent should we use for this? Yeah, exactly. It's a Markovnikov addition. It's exactly what we saw. Stick the bromine on there. Now we want to do another elimination. That's an E, probably an E. We could do an E2 or an E1, right? You got a really good tertiary carbocation. Yeah. No one would make that out of that. You just buy the other thing. But that normally we do lose a lot of stuff. It's not unusual for us to start reaction like sequences with like hundreds of grams or kilograms worth of material, and 15 steps later we're down to milligram amounts to a final drug. That's normal. A lot of the early steps in synthesis actually are called bathtub chemistry because you can literally do them in a bathtub. I have run a reaction in a metal garbage can before because you can throw in there, I don't know, 100 liters, 200 liters of solvent. Yeah. So I'm trying to replace that with like a fancy exact. I like that one. I like Emmanuel's idea. So Emmanuel's picking a big, bulky base super ball that's going to do the Hoffman elimination. And I do appreciate that you guys are trying to use like really simple transcription to talk about more complex things. But yeah, terbutoxide. Probably in terbutanol. You can pick some other solvent if you like, though. You want to do a proper E2, you can use an aprotic solvent. Cool. I'm good with that. Okay. Now we need to finish off our synthesis and add iodine. So how do we go about doing that? I like Keith's idea. The BH3, Andrew, works for water, but not for any. You need the oxygen. You can't do it with any other atom. So radical. I think Keith had that typed into his chat window, ready to hit go as soon as the question came up. That was really fast. So you wanted a radical reaction, and you want to do the anti-Markovnikov addition of HI. So this is a hard problem. This is not an easy problem. But every one of the steps is a purely logical deduction. It is purely how can I move? The first question is how can I move that handle around? And literally that is what we spend a lot of time doing in chemistry is how can we get this carbon to react and not that carbon? And what do I need to do to manipulate my molecule to get that to go? We have a limited toolkit here, so we're kind of walking out halogens around the molecule. And we can do that because we have this matched set of reactions where we can do the Zaitsev or Hoffman eliminations, and we can do Markovnikov and anti-Markovnikov additions. And that creates a complete toolkit to migrate things around molecules. But as you do more of these things, you start going, okay, well, I can, play around with this CH bond versus that CH bond somewhere completely else in the molecule by carefully tuning my conditions and my reagents. Completely overwhelming to do it here, but all the principles that drive that, all the reactivity principles that drive that, you've learned in this class. Like, I will sit down with my grad students and postdocs, and we will talk about the stuff we have talked about in this class. The decorations are more complicated. The reagents are more complicated, but it all comes down to Charge stability and resonance and accessibility. It depends what I ask. So if I probably would not ask you for all the mechanisms for all of this because there's enough going on with this question. But if you need to do the mechanisms, you need to do the mechanisms. I would actually say I propose solvents. So propose conditions, which include solvents, is what I would write. If I just said give me reagents, then you just give me reagents. You don't need to give me solvents. So it's never wrong to give more information, unless your more information is really wrong. Like if you're proposing that you do all these reactions in hexanes, I'd go you can't do some of these in hexanes because the reagent would crash out. Well, this example, that's what we're doing, Anita. Generally, I've done this once, like sort of flip a double bond. I've done that once usefully, like to make a drug. Other than that, normally we start with something else because normally it's just too inefficient. But for this course, this is kind of an example of what we could be doing. Yeah. Cool. Could we do an alkyne radical initiation? So BH3, because it's a halogen. So the BH, so Mariam said, could you please repeat what BH3 when working in? Because BH3 it goes with water. So you add BH3 and H, and then you add the hydrogen peroxide and the sodium hydroxide. So you're replacing the boron with oxygen. Now, let's say you did do that. Because you could do that. So let's run with Mariam's example. And so we have this, and because somebody else mentioned this too, and it's not wrong. It's more steps, but you know what? This isn't all about how efficient you can be. So let's do BH3. So what you would get is you would get boron here. You get that. Then the way to break this off is, I think there is a way to do this with halogens. I'm not 100% sure. And so if you use some chemistry that we haven't done in the course, you do need to put a reference in, but you can do that in the exam. That's fine. You'll just need to reference it. Otherwise, my GAs will think it's wrong. But I think you can actually do this with halogens too, but we haven't talked about that. So let's follow up with what we have talked about. So you'd have an OH there. But I want an iodine there. I don't want an OH there. So how can I do that? Well, what we did also talk about was we could turn that into a tosylate or a mesylate, whatever, one of these great sulfur thingy leaving groups. We use a weak base. Some solvent, whatever, who cares? And we convert that into a really good leaving group. And then we know that iodine is very, very stick-like. And so if we treat that with sodium iodide, we would get the iodine doing an SN2 on this position, displacing the oxygen. That will give us our product. So you could go that route, but you would just need to, kind of need to add something else in. But you do have the tools to make use of that as well. So with a lot of these, there's no one right answer. There's multiple right answers. You can, but then it's a primary leaving group, and normally under those situations, you can't have I minus in the presence of a H plus, because you won't protonate the OH in the presence of the I. And so what will end up happening is, and you're not going to generate a primary carbocation. So normally you need a better leaving group. You need to kind of activate under basic conditions. Because that you'd be looking to try and make a primary carbocation in that way. Yeah, we covered this when we were doing SN2s or earlier. Yeah, so this kind of thing is something that we discussed, was these nucleophilic, converting alcohols to better nucleophile electrophiles. Okay. So the last thing, what I'm going to do before calling it for a day, is I just want to discuss the example that did come up. It's a careful balance, Nadia. So Nadia asked, off topic, how do you know if induction or hyperconjugation is more stabilizing for a charge? It depends how big the difference. Yeah, it depends how what the inducting group is. It depends how far it is, and it depends what your differences between your hyperconjugations are. Everything is kind of in balance. I am going to. Why do we favor E1 over SN1 when we have resonance? From Fatima, that's a really good question. And so what Fatima means is, if you have an example like this where you make a carbocation and you have a double bond present, you're going to do the E1. Because E1s and SN1s are kind of in balance. You know, they're kind of very similar. You know, molecules trying to decide if it wants to do one or the other. But if there's double bond around, suddenly that new double bond you're making is a lot more stable because you have resonance with those two double bonds. And so it's a lot easier to make the double bond because this hydrogen here just became a lot more acidic because as soon as you make the double bond, that double bond's in conjugation. So you tilt the balance. Where the SN1 and E1 are kind of close, now they're not. The E1 suddenly becomes a lot more stable because of this conjugation. Yes, Mohammed, you're right. So Mohammed said the CF3 is directly adjacent. It's really going to have a massive effect. And if it's further away, hyperconjugation takes over. Yeah, absolutely. So I'm going to basically bogart the example I just drew there. And let's say we made this radical. This is flat. This radical here, this carbon here is in a p orbital. But this, and so it has as far as the orbital is concerned, that's a 50-50 chance of the top or the bottom being attacked. But we have something big blocking the top face. And so it's not going to be a 50-50 percentage of the bromine adding from the bottom or the top. It's going to preferentially add from the bottom because when it does that, the bromine doesn't need to navigate past that isopropyl group. I'm not. So, 3 Budriahi, I am not going to try and balance them. I'm not going to try and give you something that's really, really close. If I do, the question will probably be discuss why one or why the other. I'm not going to ask you to decide which one, but I'm going to ask you to discuss with me why is one favored, why is the other favored. But there wouldn't sort of be give me the right answer and then you guess wrong and you're wrong. It's not going to try and balance that too closely. Okay. I think that I got through my examples today. I'm going to post these slides now to Blackboard. I'm going to see if anyone has anything in particular they want to go over for Monday. I have not started writing the exam, and I'm not going to start writing the exam until after the last class because I don't want to teach to the exam. Because then I have no idea how I'm going to ask in the way of questions. And that's just generally how I do this. Yeah, I will be posting the chats from Wednesday and today. I don't quite understand the question, Mariam. What's with the circles? I was just circling things when I was talking. I don't remember what it was. The practice exam is open. So I did two things. One is I posted the practice exam. The practice exam requires a proctor password. You need to insert that password. I'm going to probably have the same thing. I'm going to send out the password before the exam, like a good couple of hours. So check your email. Um, and but that shouldn't go active till the like my choice is basically have a password or have a proctor sign each of you in individually, and that just sounds like hell. So I'm going to do a password. It's just, but the exam's not going to be visible to you until the start time, which is going to be 6 p.m. on December 12th. The multiple choice questions are going to be a whole lot easier than the Mobius questions. Does using an F2 instead of BR2 have any effect? If you notice, I've really been avoiding F2. I've been using CL2, I2, and BR2. F is different. F is just weird. So it doesn't quite react the same way. No, you will not be monitored during the exam. That's creepy. Yeah, I haven't heard anyone bitching about 6, so we're doing 6. No, we'll get HF maybe, but not F2. F2 doesn't actually exist. It kind of burns through absolutely everything. There won't be part marks on the multiple choice for the exam. They're not that kind of question. So the practice. So there's 2 practice exams. One is you can practice as much as you like. It's posted as an assignment, but it allows you to practice uploading stuff. And it asks you to go take pictures of your pet or something. Yeah, we do alkyne radicals next class, Kevin. I'll do that. Yeah. Laura, if you have a specific question about assignment 3, we're out of time today. You can come to my office hours. Office hours are every day next week, 9 till 10 a.m. I will post about that. I'm just scrolling up. Mariam is really focused on the fluorine. So yes, it does. So Mariam, effectively, it doesn't matter too much. All the polygens are exact the same, just fluorine's different. So I'm avoiding it because it's kind of lying to you, but it would work similar. Okay, I'm done.